Okay, we're going to get started with homework 5, part B. Using mass and energy balances coupled with the Lewis relation, derive the differential equations for how water/air temperature and molar concentration of water in the air varies through countercurrent cooling tower. Okay, so what I have here is just a diagram of a cooling tower. We have air going in the bottom and out of the top, and then we'll have our water going in the top and condensing down our film or our little cooling plastic things, and then coming out cooler on the bottom. On our right here we have DZ, and then we have our three things that we're going to have to solve for our Excel. And then we have our liquid flow, in which is going to be defined as L in kilograms per meter squared second, and our airflow, which is G in meters cubed per second times meter squared. And we have here, I just have the superficial velocity is equal to the airflow as it is volume over seconds meters squared, which is what our superficial velocity is, or volume over velocity, I guess. Okay, so still okay, all recording good. So before we hop into Excel, we need to define our differential equations that we'll use like we did for homework 4. And we're going to get started by doing thermal energy. So we can I'm going to need more space. Let's move down. So our thermal energy is going to be it's going to be defined as L times our CP value times our area, and then we're going to have that equal to times our A times our area height, and then our delta T dz, and then we're going to have that plus x, similar to what we did at the first part. This time we're going to have delta C instead of delta T dz. Okay, that looks good, and now what we're going to have to do is rewrite this expression. So we're going to rewrite it as over dz, so we're going to have dTW over dz. Let me see if I can see the whole thing. There you go. That's going to be equal to our AN times our delta T, or sorry, delta A, or AH, not N. Kind of looks like an N. Minus T air, delta T over, and we're going to have to divide by L CPW. And then we'll get, we have to add over our other term, and in the numerator we're going to have, this light's flickering, we're going to have our gamma, A, K, is there a way to dim this? There we go, that's better. Times, our AKC, and then, sorry, my arm's blocking the iPad screen I need to look at, times our PSAT over our RTW, and then we need our minus C air here, and that's going to be all over the same denominator. Okay, so now we need our change in our vapor concentration for our next step. Oops. Yeah, so I'm just gonna turn my iPad so I can write better. So now, like I said, we're gonna need our change in vapor concentration. And that's going to be equal, or not equal to, but like, alike is d G A, hold on. Yeah, G A C air. Yeah, and that will be equal to A. Okay, yeah, that makes more sense. I was so confused for a second. KC delta C dz. And this is where we can write our CW is equal to our PSAT over our RT. Cool. And then that can just be rewritten as our differential C air over dz is going to be equal to A over G KC our PSAT RTW. Oh wait, we still need to add our constant, or not constant, but our other term. And then that's going to be times, or wait, yeah, times, right? Air over dz. And then we can rewrite, oh wait. Yeah, wait. Ooh, what did I do? Okay, and then when we rewrite this term here, it's going to be equal to, I guess, this term technically. It's going to be equal to, sorry, this kind of looks like it goes along with this. This is a whole nother thing. So when you simplify, we're going to get, AH over, because we're going to need GPC air. I know what that means. Over P, yeah, RT, okay, yeah. Okay, and then we can add this term back into our differential term, and we're going to end up getting, actually, we're going to get a dTW over dz. It's going to be equal to AH over, oh, we're still going to need times delta T over LCPW plus XAH over rho CPW. Then we gotta multiply. So I'm gonna get rid of that term. Minus here. To get rid of the denominator. Okay, and then finally we can do our last term, which is going to be our dt air over dz is equal to AH over dz, or wait, sorry, not over dz, over rho cp air times g times tw minus t air dz. Cool. So we have that term, we have our term here, we have our term here. Okay, cool. So that just was how we derive differential equations to solve for what we're going to be using in Excel. Okay, we're back. I did set up the Excel, but first we're going to just go over all our constants and everything. So we have using Excel and B1 simulate air temperatures and molar concentration for water in the air for a cooling tower with inlet air of 30 degrees Celsius, inlet water at 50 degrees Celsius. Water flow of 10 kilograms per meter squared second, superficial air velocity of 5 meters per second, specific packing area of 100 meters squared per meters cubed, heat transfer coefficient of 50 watt per meter squared Kelvin for inlet air relative humidities of 10 and 50. And then after we do that first part, we will compare cooling tower height necessary for each inlet air condition. So here's Excel I set up. I already added our constants and just kind of an outline so I don't get lost, because I've been getting lost easily. So here we have our constants up here, like our A air, B air, C air that were given. And then we have our constant R, our DZ, which is the height of our tower. Air in, water out, which we'll need to solve for these that are empty. RH air, rho air, CSAT, C air in. We have our length, or we have our L, I should say. We have our G, and then all these other ones we got. So, first one I'm going to do is I'm going to add, actually, let's do that after we solve all these. I will make them formulas because I don't know if that would mess up anything. So here we're just going to do Antoine's equation quick to solve for RP set. So we know that is going to be equal to 10 to, and then we got our A, B, C, A plus B over C plus T. So we got our 10, and then we got A air dot, right? Okay, yeah, A air dot, and then minus, and then we have our B in the numerator. So B air dot, okay, I was making sure that was working. Technically they're not formulas right now because of the, but yeah. And then we'll have B air dot, and then we'll have divided by, we'll probably need another parenthesis because Excel. C air dot plus, and then we need our T, and our T that we have is, we don't have it here, so we're just going to guess 100 degrees Celsius, and we're going to need 3 of those, and then we're going to have to add a conversion factor of, around, from like mmHg to Pascal. So we'll have times 101, what is it, 325 over 760. I had that written down because I wasn't too sure what that conversion factor was. Okay, formula is missing a parenthesis. Okay. Formula is missing a parenthesis. 1, 2, 3, 4, 5. 1, 2, 3. What's missing? Like, there we go. Name. Let's see if we make these formulas, it will work. So we're gonna go formula, create from selection, left column. Okay. Cool. So we got our correct value. I'm assuming. I hope. I can check later. I'll want to cut if we're right or not. And then so now we have that value for our Antoine's. So I'm just gonna just add that there so I don't forget. Okay, so now we can solve for, what do we want to start with? Let's start with rho air. Yeah, let's start with rho air. That was loud. So we're gonna need 0.29 times 1, 3, 325, 325. I just know this is going to mess up, so I'm just adding them now. Then we're going to have that divided by our r dot times, or I guess I can type it. I don't know why I'm doing that. Our r dot, and that is going to be multiplied by our t air in. Oh my gosh, I need to stop doing it. Oh, it's probably because I don't have an equal sign. That's why I can't do it. Okay, we have, there we go. Okay, cool. Okay, now we can solve for our, where is it? Yeah, here we go. I couldn't find it for a second. Okay, and that will going to be equal to our h dot divided by our rho air air dot, and then times our cpa dot. Looks good. And then we can just solve for our final values that we still need. So we got T water out, CSAT and C air in. So let's just do CSAT first. So that's going to be equal to 10 to the, this is just kind of intones, but not really. Why did I say that? No, it's not. A air dot B air dot divided by C air dot plus T air in minus our Kelvin. I mean, I guess it is Angels. And then we're going to have 101.325 divided by our MMHG times our R dot, right? Yeah, times our R dot times our T air in. Sure. And then we can do our C air in, which is, this one's simpler. It's just our CSAT times our RH here. Okay, and then finally our last value, which is our T water out. I guess we'll fill that in eventually later. So we're gonna have to make our counter like we've been making. So we go here, home format, I would think. Is it format? No, it's this right here, fill thing. Series from 1 to 1000 columns. Okay. I'm just gonna check. Okay, looks good. And then for our step counter, we're just gonna do, it's gonna be our counter times our DZ. Yeah. And then we can drop that and it should go to point. Oh, there it goes. Should go to 5. Okay, looks good. Okay. So we're gonna do our C air in now. Okay, now we can put our C air in. So why do I keep saying our C air, which is gonna be our sea air in. Our TW, what is it? Our TW, which is going to be T water in, equal to T water in. T air, which is equal to T air in. Okay, looks good. And then our PSAT, what we're going to do is we're going to have to do 10 to the, this one's going to be, I have written down because it's kind of long. So we have 10 to the A air dot minus B air dot divided by, this is just Antoine's equation. I could have done it without it being written, but this part is kind of confusing. Times our TW, that's the part I was a little confused about. 273. And then we need to multiply it by our diffusion. Multiply it by our unit conversion for mmHg to Pascal. Okay, and then finally for our CDiff, we're gonna have our PSAT divided by our R dot divided by our TW minus our C air in. I'm not sure if that looks too right. I'll be back. Okay. Oh, oops. Okay, guys, I found the what was wrong in our Excel sheet. There's like 3 errors that I made. This was our H was supposed to be a 50, not a 5. That was 1 error. I forgot a 0. In our CSAT, I believe it was, formula, we had a multiplication sign here instead of division sign, so that threw everything off. And then I added our T water out, and then I had an incorrect value in one of these cells. I'm not sure which one it was. It was one of these two, and I didn't have, I had like the wrong reference cell. Anyway, so we're gonna move on to our TW. I also have this one down because it's really, really long. So we have our A times H. Okay, looks good. Times our L dot. Oh, oops, sorry. CPA dot. Lambda multiplied by A dot times our H dot divided by our rho air dot. I don't know if actually I can just look up top. I don't need to see that. Times our CPA dot, and then that's close parenthesis times our 1 over L dot times our CPA again. Hopefully that is good. I'll check it when I'm finished all of these. Or actually, I'll just check it now. Okay, I'm back. This was a little wrong, or this was wrong, but it's because I just had CPA instead of CPW. So all good. Okay, so we're gonna move on to D air now, and that D air is equal to our A dot multiplied by our KC dot close parenthesis divided by G dot times our I believe are Antoine's. Or no, not Antoine's. Our C diff. Cool. And then our DT air is equal to our A dot as well times our KC2 divided by G dot times our T water minus our T air. Is that in parentheses? Yeah. Probably. Something's getting 0. Because like 0 minus 0 times 0. Maybe that's how it's supposed to be, perhaps. I don't know, we're gonna keep moving on. So we're gonna move on to Euler's rule, our equation. So we know it's gonna be the top plus the step times our air. And then the same thing for here, top plus step times. And then it's going to go to 0, or 303, I guess, yeah, because we add 303. But that's not right, so I'll have to check that. But I'll check it when we get back. So I'm just going to drag these down, and then we'll go all the way down, and then I'll try to figure out what I have wrong with my DT air. Drag these down. Oh, this didn't drag down. And we will double click. Okay, and we're starting to get zeros, I'm assuming because of that. I don't know, we'll see. So I'm gonna be back, change the DT air, and we'll see what the air was. Okay, I'm back. I'm not sure where I left off because it's been over an hour and I'm still recording the same session, so I'm kind of just gonna do a recap on what I believe was wrong. So after doing our 3 steps here, I was multiplying them by the wrong differential cells, and I figured out that was my issue, and then there was still an error after that, and it just came down to my KC value here, and I think it was literally just a rounding error that was causing everything to go wrong. So it's been like 30 minutes and I was running solver to make sure it was working, so hopefully it is. Yeah. So we finally got our values here. So down here we do have a value of I at 68,000 and some, which is what we're going to use in our sum squared value to run solver. So I already have it up here when I was running it off camera to make sure it was working. So I have that number, and what we're going to do is we're going to take that number, we're going to take our T water out, I believe, subtracted by this number, and then we're going to square that. And we get this very large number, and then that's what we're going to use in solver. So let's open solver. We already have the right to solve because, again, I was testing it earlier. And then, yes, for our variable cell, we're going to have T water out, I believe. Okay. Hopefully do not converge. Okay, I'll be back again. Okay, I think we used solver, and we got our values for RTW. So finally, the last part of the homework would be to compare the cooling tower necessary height for each inlet condition. And basically what this is getting at is the Oh. Okay, so I have to do this really. Oh, okay. Okay, I'm back. I'm gonna have to do this really fast because I ran out of iPhone storage. So the last thing we have to do is compare the cooling tower and necessary height for each inlet air condition. So basically, what I'm just gonna explain it really quick is that as your height increase or decreases, your cooling tower is going to not cool down the water as much. So kind of what we have on our Excel here is when like our height lowers, so let's do like 25, I guess. Yeah, you can see that our values are dropping at a significantly lower rate than before. So